Hello, everybody. I hope that everybody has had a really relaxing spring break. Probably not too eventful, seeing as our spring break this year took place during quarantine. But nonetheless, I hope you guys enjoyed it. We're able to rest, get kind of a break in, and maybe take a break from all the craziness that's going on in the world right now. So we are just going to keep on moving through reviewing our content. Just a few reminders. I'll be posting lessons Monday, Wednesdays, and Fridays. Since you guys are A/B day classes, I'm not going to overwhelm you with the lesson every single day. So you'll be getting new lessons Monday, Wednesday, Friday. I think we're going to start doing FRQ Fridays. So Monday and Wednesday we'll kind of have review content where you guys review just the material that we've gone over, and then on Fridays we'll practice doing FRQs, and I'm looking into ways to do that without you guys just straight writing essays all the time. So I'm looking into making those more like discussion boards and things like that. So we'll probably give that a go this week, but for now we're going to start with Unit 4. We wrapped up Unit 3 before we went to break. So we're going to start today with looking at the essential knowledge from Unit 4, which was our Earth systems and resources. So this was all of like the basic Earth science stuff that you learn in a typical like freshman Earth science course. So we're starting Monday, April 20th. So I've broken this down. I've put all the essential knowledge into one PowerPoint that I'm going to link for you guys, and then I'm breaking it down by Monday, Wednesday, Friday. So today we're going to start with plate tectonics. So as a reminder, convergent boundaries can result in the creation of mountains, island arcs, earthquakes, and volcanoes. So remember, a convergent boundary is where you have two plates that push together. So basically, the lithosphere of the Earth, right, the top portion of the crust, is broken into plates. And these plates move, right? And the reason these plates are moving is because they're being moved by the convection currents that occur in the mantle underneath the lithosphere. Okay, so that magma, it gets to the surface, it cools down, it becomes more dense, it sinks. As it sinks, it warms and then becomes less dense, moves up, and then it moves in this circular motion. So these convection currents are what moves the actual plates themselves. And then with our plates moving, we have these boundaries happening. So if there's a convergent boundary, the plates are coming together. All right, divergent boundaries, if you diverge, you're moving apart. So divergent boundaries can result in seafloor spreading, rift valleys, volcanoes, and earthquakes. So if we take a look at this, volcanoes can occur along both convergent and divergent boundaries. So just because, there are crusts coming together or moving apart, it doesn't mean that you can't see similar land formations. The biggest thing, like differences with a convergent boundary where you have two plates coming together, you're going to see mountains. That is specific to convergent boundaries. And then seafloor spreading is specific to the divergent boundaries. And then transform boundaries is where we get a lot of our earthquakes, most of our earthquakes, because here you've got two boundaries that are sliding past one another. And when that happens, tension and energy builds up, and then it's released kind of like a rubber band. So if you pulled back a rubber band and you had all that tension in it, and then you released it and it snapped back, that reverberation is kind of what causes an actual earthquake. So there are maps that will show the global distribution of plate boundaries, and those can be used to determine the location of volcanoes, island arcs, earthquakes, hotspots, and faults. So again, we know that these different land formations take place at the different types of boundaries. So if we know where those boundaries are, we can make predictions about what kind of land formations we'll see there. And then earthquakes occur when stress overcomes a locked fault, releasing stored energy. So a locked fault is basically just when you've got these two plates that are grinding against each other, and that energy is building up and they're not necessarily moving. And then once it moves and the energy is released, it reverberates and it creates that earthquake. Here's an example of a map where you can see the different boundaries. So here's divergent boundary. You can see they're kind of these straight lines. So we've got divergent boundaries here along the East Pacific Plate and the Nazca Plate. So these are moving away from each other. A convergent boundary has these triangles on it. So here we've got the Nazca Plate and the South American Plate. Those are divergent boundaries. And here we see mountain chains and volcanoes, right? Which is what we would expect to see along a convergent boundary. Transform boundaries are just the one single solid line here, and then you see your little land formation, so your mountains, your volcanoes, and then the arrows are showing you the relative movement of the plates. So if you were to be presented with this, you should just be able to tell, okay, I know that this is a divergent boundary, or I know that this is a convergent boundary, and then you should know kind of what would occur along those boundary lines, because you could get an FRQ. We already know that one of your FRQs is going to be experimental design, but you might possibly see one where they give you, you know, a diagram of a boundary image like this and say, okay, what's happening along this plate? What would you expect to see there and why? Okay, so it's helpful to know how to look at one of these, read it, and then based on your knowledge of what occurs at each boundary, be able to describe kind of what's happening there. Okay, so the second thing we're going to review today, the second and last thing, is going to be soil formation and erosion. So soils are formed when parent material is weathered. So weathered just means broken down, transported, and then deposited. Soils are generally categorized by horizons based on their composition and organic material. So remember, when we're looking at soil, there are different horizons of soil. So at the very bottom here, we've got our unweathered parent material. Okay, so this is going to be basically your bedrock. So remember when a primary succession happens and there's no soil at all and everything gets wiped out, this is what you're left with. Okay, so this is step one. So then we have our C horizon, which is partially altered parent material. Your B horizon has an accumulation of clay. Your E horizon has light colored mineral particles. And then your A horizon has mineral matter mixed with some humus. And then your O horizon has loose and partly decayed organic matter. So if you can just remember, O for organic is your organic matter. Now your top soil, where, you know, we plant our agriculture and where most of the life is in soil, is composed of your O and your A horizon. And then your true soils are from your B up to your O. And we say true soils because, again, this unweathered parent material is not really organic. It's just kind of the basis of soil. It's rock. It's not living. It's got minerals in it. So when we talk about soil as a living system, this is just kind of the base. And then from here up is where like really all the good stuff happens. So a reminder about just particle size when we talk about soil. Remember, soil can be categorized based on its composition. So we have sand, silt, and clay. Those are our three particles that will compose soil. Sand is going to be the largest. Okay, so sand is our largest particle, followed by silt, followed by clay. Now, these different sand or different soils will have different water holding capacities based on their sizes. So a water holding capacity is just the total amount of water soil can hold, and that varies with different soil types. So water retention does contribute to land productivity and the fertility of soils. So if we think about clay, if we have a bunch of clay soil in an area, clay is very small and it's very densely packed, so it doesn't really typically allow water to move through it very quickly. So clay typically won't be good. A pure clay soil would not be good for agriculture because the soil would not be able to seep down and get to the roots of plants and allow them to grow with what they need. So you kind of want to have a good mix of all three for agriculture, because you want some clay in your soil mixture, because clay also is really good at holding on to water. Because the water can't move through it, it tends to become waterlogged in a way and hold on to a lot of it. So you want to have a good mix so that, you know, water doesn't completely run through your soil. You want it to be able to run through to get to the roots of your agriculture, but you also want it to be able to kind of stick around for a little bit to make sure that those plants have enough time to take up that water. You know, on the opposite side where you have sand, if you guys ever go to the beach and when you were younger and filled up a little sand pail with sand to make a sandcastle and maybe ran some water through it, it just kind of completely pours through it because it's really large. There's not a lot stopping the water from seeping right through it. So the particle size and the composition of each soil horizon can affect the porosity, permeability, and fertility of the soil. So porosity is basically how well it absorbs the water, and then permeability, how fast does the water move through it, and then fertility, how supportive of it is it of life. So there are a variety of methods to test the chemical, physical, and biological properties of soil that can aid in a variety of decisions, such as irrigation and fertilizer requirements. So my recommendation would be going back into your textbook, because you guys should all have your textbooks with you, and look back at your soil chapter and kind of review those properties, because I have seen FRQs in the past where they kind of ask you specifically to name a test that you could do to test the soil. And basically you would have to just come up with like a hypothetical situation of how you would do it, what would it tell you, and then where would you go from there. And then soil texture triangle is a diagram that allows for the identification and comparison of soil types based on their percentage of clay, silt, and sand. And you guys, I bet, do remember the soil texture triangle, but that's kind of what we're going to end with today. And it is what you guys are going to practice with today, because I have seen soil texture triangles in multiple choice questions before. I'm not sure if they would be in your FRQ, but we know you're definitely going to get 2 diagrams. So who's to say one of your diagrams would not be a soil texture triangle? So let's just review how to read one of these. And I'm also going to link a video of somebody else showing you how to read one as well. And then your independent practice for the day is going to be an activity where you just use the soil texture triangle to determine the percentages of each particle in the soil. Okay, so if we look, we've got our percent clay on the left hand side, you've got your silt on the right hand, and then you've got your sand on the very bottom. Now remember, when you do this, your percentage of these particles in your sand always have to come up to 100. All right, so if you've got 30 clay, 30 silt, and then you would have to have 40 sand, okay, because 30 plus 30 is 60. All right, and then you'd have to have a percentage of sand to add up to 100, because your composition has to be 100%, so you'd have to have 40% sand. So when you're doing one of these, if you want to figure out what the soil texture is, you've got to just basically just follow along where you start based on your different composition. So like earlier I said, let's hypothetically we had a percent clay of 30, okay? So you would start with 30, and you would follow this line from 30 all the way across, okay? And you find where your lines from your silt, clay, and your sand intersect. So your clay goes from left to right. Now your silt goes from top to bottom, okay? So I said that our clay was 30, and then I said that our silt was also 30. So you would come up and find your silt, and you would follow the silt line at an angle down, okay? So clay goes over, and then silt comes down. And then your sand, you would want to find your sand. Remember, we said it would have to be 40%. So you would find your 40% sand, and you would follow it up. Okay, so you would follow the sand up, and you would find where they all intersect, which looks like it would be at clay loam. So the answer for a soil texture that was 30 clay, 30 silt, 40 sand would be clay loam. Okay, and just a reminder, loam is going to be an even mixture of all 3 of them, and then so loam would be typically what's best for agriculture. Okay, so your independent practice today is going to be looking at soil texture triangles. I'm going to link one for a reference so you can open it and just have it with you, and then you're going to open up the little quiz that says soil texture triangle. Take that, it'll give you immediate feedback. I'll set it to where you guys can have 2 attempts at it. And if you have any questions, let me know. Just make sure when you're doing it, you're making sure that your percentages are adding up to 100%. Okay. If you guys have any questions, reach out to me. I hope you guys had an awesome spring break, and I hope that your studying for your AP exam is going really well. So I will be back checking in with you guys on Wednesday.